I'd like to thank everybody for joining us. Welcome to today's CNCF webinar, Securing and Accelerating Kubernetes CNI Data Plane with Project Antrea and NVIDIA Mellanox ConnectX SmartNext. Don't say that too many times fast in a hurry, but I managed to get it out. My name is Lachlan Evenson, a Principal Program Manager at Azure and CNCF Ambassador. I'll be moderating today's webinar, and I would like to welcome our presenters today. We have Antonin Bas, maintainer of Project Antrea and staff engineer at VMware. Ite Ozuri, director, product management for networking at NVIDIA. Cody McCain, senior product manager, containers at VMware. And Moshe Levy, senior staff engineer at NVIDIA. A few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Feel free to drop your questions in there and we'll get to as many as we can throughout this webinar or towards the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that will be in violation of the Code of Conduct. Basically, please be respectful to all your fellow participants and presenters. Please note that the recordings will be posted later today to the CNCF webinar page at www.cncf.io/webinars. And with that, I will hand it over to Antonin, Ite, Cody, and Moshe to kick off today's presentation. Welcome. Over to you, gents.
Thanks so much, Lachlan. And we want to thank the CNCF for the opportunity to share the exciting work that we in the Project Antrea team are doing to improve and accelerate CNI in Kubernetes. As Lachlan mentioned, my name is Cody McCain. I'm a product manager for container networking at VMware. And today I have with me Antonin Bas, one of the maintainers of Project Antrea. He is going to be taking us through an introduction to networking in Kubernetes, as well as a deep dive into Project Antrea. We also have today Ite and Moshe, both from NVIDIA, and they're going to show us the work that they've been contributing to the project in regards to hardware acceleration and the exciting way that we've been able to speed up the data plane in the CNI product. And then finally, we'll close the webinar with a demo and with a look at our roadmap and some of the exciting features that we have planned for the remainder of the year. So without further ado, I'd like to hand over to Antonin to take us into container networking.
Thanks, Cody. Let's take a look at the Kubernetes cluster networking and a quick recap first. So Kubernetes expects a network plugin to provide the following three network communication paths. The first is pod to pod. So according to the Kubernetes network model, each pod gets its own IP address, and all pods on a node can communicate with all pods on all nodes without any address translation. And this is really the main responsibility of a Kubernetes network plugin, which we also call a CNI plugin. It's building this pod network and ensuring connectivity between all pods. The second problem to address is pod to service traffic. And this consists in being able to load balance traffic directed at one IP address allocated by Kubernetes across a set of pods running the same application. And usually this is achieved by having the network plugin collaborate with kubeproxy, which is an upstream Kubernetes project. And the last problem that needs to be addressed is external to service traffic. How can the services implemented inside the cluster be exposed to the external clients? And this is a pretty large topic, and there are multiple ways in Kubernetes of exposing the service externally, for example, using node port. And this is a different way of looking at Kubernetes networking here. It shows the different networking components' responsibilities and how we can organize them into three different layers. The bottom one is, of course, the underlying network fabric, how the nodes in your cluster can talk to each other. And if you are deploying Kubernetes on virtual machines, using virtual machines as nodes, this network may itself be a virtual network built upon a physical underlay. At the second layer right above, we include the responsibilities of the Kubernetes network plugin, or the CNI plugin. We also include layer 4 service load balancing and cluster DNS, which provides DNS and service discovery inside the cluster. And finally, at the top layer, we have included ingress and service mesh, which provide layer 7 functions and rely on the networking functions that we've seen in the bottom layers. Ingress is typically used for north-south traffic. It's going to expose HTTP routes from outside the cluster to your cluster services. And service mesh is typically used for east-west traffic between microservices inside the cluster. And today we're discussing Project Antrea, which is going to provide the CNI network functionality, but we will also see what part Antrea plays in implementing service load balancing. So let's take it one step further now and look at what a Kubernetes CNI network plugin is responsible for. As I mentioned before, its main responsibility is to provision and build the pod network. But what does that entail in practice? Well, for each pod we create in the cluster, an IP address needs to be allocated to the pod. And the CNI plugin will create a default interface, which is called E0 for the pod, assign the allocated IP address to it, and join that interface to the pod network. Typically on a Linux node, this is done by creating a pair of these interfaces and moving one of them into the pod's network namespace and naming it E0. And this whole operation is going to be requested by kubelet by invoking a standard interface that is called the Container Networking Interface, or CNI. And that's really where the name CNI plugin comes from. Because a Kubernetes network plugin, like Antrea, needs to implement this interface, but it also does much more than just implementing the CNI interface. It also, for example, provides network policy enforcement. As part of the Kubernetes APIs, a cluster operator can define network policies, which are going to dictate how pods can talk to each other. Remember that a moment ago, I mentioned that by default in Kubernetes, all pods can talk to each other. All pods can talk to every other pod. Well, that's going to change as soon as you define a network policy and you apply it to a pod. Because when you do that, in Kubernetes terminology, the pod becomes isolated, which means that it can now only send traffic to or receive traffic from pods that you're explicitly going to select. Not all Kubernetes network plugins are going to implement network policies. For example, if you're using a Kubernetes managed service like GKE in the Google Cloud or EKS in Amazon, the native networking solution there is not going to implement those policies. And then we've already talked about layer 4 service load balancing. And typically this is just left to the responsibility of kubeproxy, and the CNI plugin just needs to collaborate with kubeproxy, by which I mean that service traffic originating from a pod needs to be made available to kubeproxy for load balancing. But increasingly, network plugins also implement this function. And we will see later why they do that, and that it's also the case for Antrea. And now that we've done a pretty comprehensive review of Kubernetes networking and the responsibilities of a Kubernetes network plugin, let's dive into what Antrea is and what sets it apart. Project Antrea is an open source CNI network plugin providing pod connectivity and network policy enforcement with vSwitch in Kubernetes. And let's look at these highlighted terms here in orange. We have looked into what CNI means, but there is a new important keyword here, and that's vSwitch, also known as OVS. So as we dive deeper into Project Antrea, we're also going to take a look at what vSwitch is and what it brings to the table. It was important from us to the beginning that Project Antrea be a community-driven project. And I won't go into too many details now about our community activities, because I think Cody will be covering that towards the end of the presentation. But there are a few GitHub metrics here for Antrea, and we can see that it has picked up some momentum despite not being 1 year old yet. And one of our main goals with Antrea is to provide a good user experience. And that means that we want Antrea to be easy to deploy. You can do that by applying a single YAML manifest. And that we invest a lot of effort developing new monitoring and diagnostics tools. So first, where can one run Antrea? And our answer is that we want it to run anywhere Kubernetes runs. And really, that's just part of our focus on providing a seamless user experience. And that means we want to support the private cloud, whether it's hosted or on-prem. We want to support the public cloud. And here we include both Kubernetes managed services, such as GKE, EKS, or AKS, and what we refer to as do-it-yourself cluster, or DIY clusters. And by DIY, we mean a cluster that uses nodes provisioned on the public cloud, for example, on EC2, but which you manage yourself. So for example, a cluster that you're going to create with a tool like KOps, or with Cluster API, or directly with kubeadmin. And in terms of the Antrea implementation, there are some differences between manage and do-it-yourself clusters. And finally, we want to run Antrea at the edge, typically on bare metal servers. An interesting fact about Antrea is that we support both Windows and Linux, and we try to achieve feature parity between Linux and Windows. Windows support, as you may know, is relatively new in Kubernetes and is still a work in progress for a lot of tools such as kubeadmin. But we try to provide a good experience for people who want to deploy Kubernetes with Project Antrea on Windows nodes. And that's something we're continuously improving upon since we first added Windows support a couple of releases ago. And finally, it's still a work in progress, but for the edge use case, we also want to support ARM hosts in addition to x86 hosts, but we're still figuring how to validate ARM support as part of our CI testing. And now, as promised, let's review what vSwitch is and why we decided to use it to implement the data path for Project Antrea. Well, OVS, as the name indicates, is a virtual switch. It's actually a programmable virtual switch. So as a virtual switch, it's used to connect VMs, typically through TAP interfaces, or containers, typically on Linux through VS interfaces. OVS has been a Linux Foundation project since 2016. It's widely used in production. I think it's been used as part of the OpenStack Neutron for a long time, OpenStack Neutron plugin. And it has a very active developers community with a lot of support from hardware vendors. OVS is very well integrated with Linux. The OVS kernel module provides high performance forwarding, and it's been available in mainstream Linux since kernel version 3.3. And that's very important because it means that OVS is going to work out of the box in practically all Linux distributions. And OVS is also supported on Windows, which makes it a great choice for us who want to build a Kubernetes network plugin that's going to work on both Linux and Windows. And for us, that means that we don't have to duplicate software development efforts because we can pretty much use the same software stack and the same packet processing pipeline on both Linux and Windows. I said earlier that OVS was a programmable switch, but what does programmability mean exactly? Well, of course, you can use OVS as just a drop-in replacement for a Linux bridge, but that's not very interesting. What OVS lets you do is define your own pipeline and choose which packet header fields to match on and which actions to take based on the result of these matches. OVS supports many protocols, and in particular tunneling protocols such as GRE, Genie, VXLAN. And thanks to programmability, all the Kubernetes networking requirements we've looked at earlier can be implemented in OVS. Pod networking, network policy enforcement, and service load balancing. Unlike the Linux bridge, OVS supports high-performance packet I/O when needed using technologies like DPDK and IPFIX. And in addition to these, several vendors like NVIDIA, for example, offer OVS hardware offloading support on their NICs. And we'll cover that in the second half of the presentation. And finally, OVS comes with a variety of tools that are interesting from a troubleshooting or monitoring perspective. For example, CLI tools to dump flows, perform packet tracing, show statistics. And because of that programmability aspect, it's also possible to customize the pipeline to build higher level user-facing tools for monitoring. This slide shows the different Antrea components and how they all fit together and interact with each other. And there are two main pieces to Antrea, which are the Antrea agent and the Antrea controller. The agent runs on every node using a Kubernetes daemon set. It takes care of configuring each pod's default network interface, the E0 interface. And in practice, that means that when a pod is scheduled to a specific node and the kubelet agent running on that node is notified, it's going to invoke the CNI interface and the API call goes to the Antrea agent, which is then going to set up networking for the pod. When the pod needs to be deleted, kubelet is again going to invoke the CNI interface and notify the Antrea agent, and the Antrea agent is going to take care of the necessary cleanup. And the Antrea agent is the one talking to the OVS bridge over a local socket. So Antrea supports different encapsulation mode based on what your underlying network fabric is like. And typically, one is going to use Antrea with encapsulation enabled, which means that the pod network is an overlay network. To achieve that, the Antrea agent is going to create tunnels between nodes using the desired encapsulation protocol. By default, it's going to be Geneve. But Antrea can also run without encapsulation under certain conditions or for cloud managed services because those services take care of programming the network fabric to support pod traffic. And the other major component is the Antrea controller, which runs as a Kubernetes deployment. It's a centralized entity which watches network policies from Kubernetes, transforms them, and disseminates them as needed to the relevant entry agent so they can be enforced. And why do we use a centralized controller for this? Well, it's to reduce the duplication of work between agents, and also we believe it scales better because now only the controller needs to connect to the Kubernetes APIs and watch for network policies. The communication channel between the controller and the agent is implemented using an instance of a Kubernetes API server. And that's a pretty recurrent theme in the Antrea design. So as much as possible, we try to reuse the technologies available as part of the Kubernetes ecosystem. And in this case, it's a Kubernetes API server library, but we also use like custom resource definitions or CRDs to define new user-facing APIs. And this slide here goes beyond the main Antrea components and look at the integrations we support with third-party tools and what kind of monitoring and diagnostics capabilities we support. And you can see them in the bottom half here. So both the Antrea agent and the controller create some CRD resources to report the runtime information, for example, the status of the OVS bridge. And that information can be visualized in Octant. Octant is a web dashboard to visualize Kubernetes resources. I believe there was a CNCF webinar a couple of weeks back by one of the Octant maintainers. Octant supports extensibility through plugins, and we have built our own plugin for Antrea. The plugin is not just used to display runtime information, it can also be used to initiate packet tracing requests through the pod network and visualize the results. And I think Cody is going to show an example towards the end. We also have developed our own CLI, which we name NCTL after kubectl. It can connect to either the agent or the controller and execute HTTP requests. And one of the most useful commands we have is support bundle, which can retrieve logs and other pieces of information useful for troubleshooting issues. It's going to package all of this in one tarball that can be uploaded somewhere. So we built this command to facilitate reporting issues that one can observe on clusters running Antrea. And finally, we recently added some metrics to the agent and controller, and those metrics can be scraped by Prometheus and displayed in a web dashboard such as Grafana. So we've seen our Antrea implement the Kubernetes Network Policy API using a controller and agent design. However, in practice, it turns out that the Kubernetes Network Policies alone are not enough for many use cases. And this is why in Antrea, we're working on building a very comprehensive policy model with some extensions. For one, we've defined new network policy CRDs for namespace and cluster level policies. And unlike the vanilla Kubernetes network policies, cluster level policies can apply to all namespaces in a cluster, not just one namespace. We also have introduced the concept of policy tiering. So the Antrea specific policy resources can be created within a specific tier, and all tiers have a different precedence. So all policies defined within an upper tier on the left side here are going to take precedence over policies created within a lower tier on the right side. And in practice, each tier will correspond to a specific role in the cluster. For example, the cluster administrator is going to get his own tier, and the application operator is going to work in a different tier. And this concept of tier provides very granular control over policy management and can help ensure that an application operator cannot override some global policies, which you may need for regulation compliance reasons, for example. And different policies within the same tier can in turn be ordered using a designated priority value in the specification. And finally, it's important to note that all of this is supposed to coexist with the default Kubernetes network policies, and we place those Kubernetes network policies in the rightmost tier, which we call the default tier. Some developers in the Antrea community are also working with the Kubernetes SIG network to explore whether the standard network policy API can be extended to include some of these concepts we've just talked about. And I think this is part of an effort called Network Policy V2, since a new version of the Network Policy API is meant to eventually come to life. To make things a bit more concrete, this slide shows the different paths that packets take when Antrea is run in encapsulation mode with a pod overlay network. So by default, we use Geneve as the encapsulation protocol between nodes. So in green, you have the pod-to-pod traffic within the same node. And in this case, it's pretty easy. OVS just acts as a traditional bridge and just does L2 switching between local pods. In blue, you have pod-to-pod traffic that needs to go through a different node. to go to a different node, sorry. And in this case, we encapsulate the traffic and send it over the underlying network. And finally, for traffic that needs to go outside the cluster, as we show in red here, Antrea is going to implement source NAT using IP tables. So the first packet, the packet first goes out of a special OVS bridge port, which we call the gateway port, and IP tables is going to perform SNAT in post routing. There's one type of traffic that we've talked about before and we don't see here, and that's pod to service traffic. So what do we do for this case? And this slide shows how Antrea currently handles pod to service traffic by default. So packets are sent through the gateway interface once more into the host network namespace. And their kubeproxy IP tables role is going to take care of layer 4 load balancing and is going to take care of performing destination NAT based on the selected service endpoint. After that, packets are going to go back through the gateway and are going to be also handled by the OVS bridge, just like in the pod-to-pod scenario we saw on the previous slide. But what I mentioned briefly earlier is that Kubernetes network plugins sometimes implement their own service load balancing functionality, and that's what Antrea does as well. And so starting with the latest Antrea release, we have an alternative implementation for service load balancing using OVS, and you can see the difference here on this slide. It's a pretty comprehensive implementation, which even supports something like session affinity. So why did we go this route of supporting like service load balancing natively in OVS? Well, the new implementation enables us to achieve better performance metrics than when we use kubeproxy, simply because we no longer need to send all packets through the gateway and the host network namespace anymore. If you look at this picture and you compare it to the previous slide, you'll see that the packet path has become simpler and shorter. That's all talk, so let's look at some actual numbers. So we ran 3 different experiments on a Kubernetes node using a tool called netperf. And we looked at 3 different scenarios. The first one is plain pod-to-pod traffic. So we use that as the baseline. We also looked at pod to service using kubeproxy, which is the old Antrea implementation, and pod to service using Antrea proxy, which is how we refer to the new service load balancing implementation with OpenFlow. We looked at 3 different traffic patterns, and I'm not going to go into too many details, but the first one, the leftmost one, is a good measure of like throughput. And the middle one, TCP_RR, is a good measure of latency. And so when we look at those results, we can see that the Antrea proxy OVS implementation achieves better performance than the previous implementation, which was using kubeproxy. And actually, as a matter of fact, the new performance is almost identical to plain pod-to-pod traffic performance. So there is no impact from doing service load balancing. And now I'm going to hand the presentation over to Itay, who's going to talk about hardware acceleration for OVS and for Antrea. I don't know if we want to do a check on questions first, if there are any questions.
We'll handle some questions at the end, or they can put their questions into the Q&A chat.
Great. Yeah, hi. Thank you, Anthony, and hello, everyone. I'm excited to present today, and thanks to the CNCF and our friends and Antrea for partnering with us today. So then NVIDIA networking team has collaborated with the Antrea community to drive our SmartNIC hardware acceleration into the Antrea project. I'd like to provide some context into the reason for enabling hardware acceleration in a cloud-native environment. So we're seeing increasing demand across public, private and edge environments for high-performance workloads, where Kubernetes is primary platform for serving those use cases. So you have the machine learning, AI, 5G telecommunication, and what have you. But those of you that are familiar with networking know that in the past, one had to choose between having a virtualized networking infrastructure with advanced policy and programmable topology together with accelerated networking. So legacy network acceleration techniques couldn't support virtualized, not to mention containerized environments. So it was really an either or all kind of a decision to make. So let's let me introduce OVS Hardware Offload technology. With Project Antrea and OVS Hardware Offload, you can really have both accelerated networking with all of the benefits of a virtualized network infrastructure. So what we've done is we've leveraged the open source construct in the Linux kernel and open vSwitch community to accelerate network performance in a way that maintain the virtual switch control plane, but only the data plane is then offloaded to the SmartNIC hardware. So by offloading the data plane to the SmartNIC hardware, we see significant network performance increase while even saving CPU utilization. Now let me pass it over to Moshe in the NVIDIA team who led the development and integration of the OVS Hardware Offload to walk you through some of the implementation aspects and also show a demo. Moshe, please. I believe you're on mute.
Hi, Moshe, can you hear us? You may be on mute.
Yeah, thank you. Sorry.
There you go. Thank you. We can hear you now.
Yeah, I was just trying to find the button to unmute myself. So sorry. Thanks, Itai. Now that you bring an introduction to the OVS Hardware Offload, now let's let's do a dive into the implementation part and see how it actually works. So typically in OVS data path processing, we have is done in the host, either in the kernel or in the user space if you're using OVS TDBK. And in order to achieve the acceleration, what we introduced is basically we're moving the data path flow processing from the host to the SmartNIC itself, and allow us to reduce the CPU utilization, to increase the bandwidth, and decrease the latency. So how do we do that? Basically, we are leveraging, OVS Offload is leveraging the SR-IOV technology. So I will talk a little bit about what is SR-IOV. SR-IOV stands for Single Root I/O Virtualization. It has a physical function, PF, which is a full PCIe function, and a virtual function, VF, lightweighted PCIe function. The NIC can expose multiple virtual functions as a network devices to the host. And the number of the virtual functions, the maximum virtual functions that are supported are dependent on the NIC vendor. Now, each virtual function has its own virtual function representative, as you see in the diagram. And the virtual function representative actually allows the switch to program it in the SmartNIC. In our case, it's the OVS. It's a way for the OVS to program our SmartNIC to do the hardware workload. You can think about it like a wire connecting two endpoints. We have one endpoint moved to the pod or a virtual machine, the virtual function, and the other endpoint, which is actually plugged to the bridge, which is the virtual function representative. So our OVS works with hardware offload. Just a little bit about that. Standard OVS flow usually is there is a first packet comes in. The packet goes to the OVS user space, the OVS vSwitch D. The OVS program the kernel data path. Then the second and the third packets comes directly to the kernel and being processed there. Now, when we're talking about hardware offload, the start is basically the same. A first packet comes in to the OVS user space. OVS now will program the data path for the SmartNIC and for the kernel. And when the second packet and the third packet comes in, basically it's now depend on the vendor NIC. If the vendor NIC have offload capabilities such as VXLAN, Genève, offloading, and connection tracking, it can be done in the SmartNIC itself and be fully offloaded. If not, we are falling back to the kernel data path, and basically we are same as software OVS. The important thing to understand is that basically no functionality lost when you're using the hardware acceleration, OVS hardware. So now talked about OVS hardware offload in the context of Antrea and basically what we did to enable that. Like I explained before, this is we are relying on SR-IOV. So basically we are using SR-IOV network device plugin, which allows us to manage SR-IOV virtual functions resources in Kubernetes. We are using Multus CNI. Usually Multus is used to enable multiple interfaces in a pod, but we are not using it like that. We just use it on the default primary Kubernetes network with Antrea to allow us to get the allocated SR-IOV virtual function. And we're still using the same Antrea project, just with the offload support that we contribute to the project. Let's go a little bit about pod creation flow without offloading. Basically, a user create a pod YAML file, provision it, Kubelet will get the request, create a pod network namespace, trigger the Antrea CNI. The Antrea CNI will create a VTH pair, basically virtual interface Ethernet in Linux. One endpoint of it will be moved to the pod network namespace and renamed to ETH0, and the other one will be moved, will be plugged to the OVS bridge. And in the offloaded mode, the flow is a little bit more complex because we have SR-IOV resources which we need to manage. So like I explained before, SR-IOV network device plugin is actually managing the virtual function resource pools and initializing it. A user create a pod YAML file requesting he wants an SR-IOV resource. When you provision the pod, Kubelet with the SR-IOV network device plugin allocate a free SR-IOV virtual function and save it in Kubernetes. Then Kubelet will create a pod network namespace and call the Multus CNI. Multus CNI will communicate with the Kubernetes API to retrieve the SR-IOV device device ID, the PCI address of the virtual function of the allocated pod, and will pass it as a CNI args to the Antrea CNI. And in the Antrea CNI, we modify the code. So if we have this PCI address, we are doing two things. One, we are moving the virtual function device to the pod namespace, and we're looking for the virtual function representer and plug it to the OVS. Now, in case you destroy the pod, of course, we are returning the virtual function to the host namespace, and we unplug the virtual function representer from the OVS point. Basically, I covered this also here. So we prepared a demo to show you how Antrea works with the hardware offload support that we have. So a little bit about the setup. The setup is 3 servers, 1 master node and 2 worker nodes. All the OS installed is Linux CentOS 7.7. We are using Kubernetes 1.18. We replaced the kernel and used the latest GA upstream kernel, which is 5.7, because we wanted the support for connection tracking. The Antrea project is based on version 0.8.0 with the offload patches. And all the servers as an NVIDIA Mellanox ConnectX 5 SmartNIC connected to a switch. In the demo itself, I will cover the following. Sorry. How to deploy the SR-IOV network device plugin, how to deploy the Multi CNI, how to deploy the Antrea project, how to create a pod YAML for VTH for a non-offload pod, how to create an offload pod with SR-IOV. We will show you some numbers running IPERF on 2 VTH pods and some numbers, performance numbers running IPERF on 2 offload pods. Just keep in mind that the benchmarking was done on my development setups, which are basically not tuned for performance and development servers. So, but it's just to give you the feel of the hardware acceleration. So I will start the demo. Okay. Okay, so this is my Kubernetes environment. Here I have 1 master and 2 workers, worker 0 and worker 1. Each worker node is worker 0 as a virtual function. You can see I have here 5 virtual functions. And on worker 1, the same 5 virtual functions. 5. This is the configuration for the SR-IOV device plugin. As resources defined, we are specifying the vendor and device virtual function. This is just the complete map of it. Provision Kubernetes. And here we deployed the daemon set of the SR-IOV device plugin. Just showing that all the SR-IOV device plugin pods get created and run on different nodes and different nodes. Now we deploy the daemon set. And we need to provide the network statement definition of Antrea. So this is the basic Antrea configuration in the CNI. Plus we just added that the network can have a SR-IOV resource defined in the SR-IOV device plugin. Provisioning the Antrea CRD or the network statement definition. Checking that multi running on all the pods, on all the worker nodes. Provisioning the Antrea project. You can see we have the controller running on and 3 agents. Basically, each agent has 2 containers. One is the OVS container, and the other one is the Antrea agent itself, making sure that everyone is running all the containers already. So this is an example of how to create a VTH pod or non-offload pod. Very simple, just image. about that. So it's running, got an IP address. And just to show that it says BTH. Okay. Now we'll see the just to show you that the OVS that's running in the Antrea is configured to hardware offload. It's just important to say that all the other offload work is completely upstream and using by OpenFlow for vendors to offload the OVS. So there's no proprietary stuff here. And this is the port spec for the offload. You can see we're requesting SR-IOV resources and provisioning the pod. Pod is running. And just to show you that it has a PCI address, a virtual function. Here, the other ones that I have. Just a second. One. So this is the performance testing for non-offload pods. So you can see I have two VTH pods here. I'm logging to the first one, showing you the VTH pod. Running IPFIX server on it, logging to the second one, which is on another node. Show you again VTH pod, running IPFIX client code. So you can see in my setup, I'm getting around 60, 70, something like that. Let's move to the offload one. So again, same setup. Now I have two offload pods, each one on a different worker nodes. Logging to the first one. This is a virtual function pod. The IP address, running IPFIX. Logging to the second one, running the client pod. So I'm also running a dump on the bus representer to show you that, first of all, I'm getting much better result here. And also, you don't see the other packets because they are going to the hardware. So basically, just see the first handshake of the TCP and the end of the connection. All the other stuff are getting offloads. And I'm getting like 4 times the performance. That's basically it. And Cody, I will switch back to you.
Thanks so much, Moshe. Let me share my screen.
There you go.
So we're pretty excited just with the development setup to get that type of performance increase with the hardware offload. We still have additional tuning to do, but what Moshe has shown today is really promising. So what I want to take you through right now is a quick review of where we are. We're, as Antonin said, only a year old, or not even a year old at this point, almost a year old. And this is a very aggressive project. We move at a very fast cadence. Right now we're releasing every 6 weeks. And even so, we've already got a lot of features that are already ready as a drop-in CNI for whatever project you have in mind. So let's look at what's available today. So Antrea can provide an overlay with or without packet encapsulation, as Antonin pointed out. Right now, we support Geneve, VXLAN, STT, and GRE. We default to Geneve if an encapsulation is needed. Additionally, we can run anywhere Kubernetes runs, and we have currently tested both on-premise scenarios and cloud scenarios, including managed Kubernetes as a service. Antrea is unique in that it accelerates service load balancing by translating service VIPs in line, again, as Antonin showed you, so that we can have a more performant translation of VIPs to their concrete pods when we do service load balancing with our Antrea OVS proxy implementation. Additionally, we already have full support for Kubernetes Network Policy version 1. In the community, we are actually contributing to improving the overall conformance testing frameworks for Kubernetes network policies, and are also collaborating on use cases for the Kubernetes Network Policy version 2 working group. Antrea is also enhancing policy options through native policy extensions, such as cluster scoped network policies. But we also take security as a really important factor too, and we provide both control plane security and additional things like spoof guard out of the box, as well as transit encryption with IPSec. One thing that we didn't get to today, and we're excited to be working with the NVIDIA team, is not only do we plan to offload the OVS processing pipeline, but also to be able to offload IPSec acceleration as well in the future. We're hyper-focused on usability and visibility, providing Prometheus metrics and monitoring CRDs to observe control and data plane health and performance, as well as several diagnostic features, including Traceflow, support bundles, and we've created both a CLI and an Octant UI to interact with Antrea. So for example, the Traceflow is new as of release version 0.8, and it allows us to do both intra and internode traffic tracing. It uses the OVS packet and feature to help user troubleshoot connectivity issues. Additionally, we are a CRD API, and so coming in version 0.9.0, we'll provide the same functionality either via CRD, the Octant UI, or the CLI AntCuddle command line utility. In this example, we're looking at a request from pod TCP STS 0, and we want to check to see if it's allowed to talk to another pod, TCP STS 2, using TCP on port 80. And the nice thing about the visualization is we actually see how the traffic traverses the OpenFlows and the OVS overlay as it makes its way from the first pod to the second pod. In this test, we look at something similar, except we change the port to 8888, and we actually see that a network policy has intercepted the traffic and denied access. And so this is going to be a great tool. Again, this is very preliminary and some of the first UI pieces that we've produced for this. But we're hoping that this is a great way to improve the usability and understanding how network policies are actually impacting traffic, and so that developers and administrators can write network policies that really align to the use cases they need to and the security postures they need to enforce. Finally, being a heterogeneous solution is very important. And again, the nice thing about OVS is it allows our implementation to be homogeneous across multiple OSs. And we already have a lot of momentum in the Windows support, and are hoping that some of you in the community will give that a download and try it out and give us some initial feedback on that. So planned features for this year. We're expecting to have IPFIX flow data export. We're going to do advanced traffic matching and pod binding. Antonin talked about our policy model and how we want to introduce tiering, both in support of multi-tenancy and delegation, so that we can provide another level of granular control for policy and allow a separation of duty and concern on who's actually implementing policy. And we also want to be aware that a lot of use cases are moving to IPv6, and we will provide IPv6 dual stack support. We mentioned the IPsec offload. We're expanding our support for Kubernetes as a service and cluster API providers. We want to make sure that, again, anywhere Kubernetes runs, we want Antrea to be able to be compatible. We're also including enhanced data path capabilities such as DPDK. OVS, by the way, supports some of these things. We've looked at SR-IOV today and how we did hardware offload using that functionality. And so stay tuned in this area because there's a lot of advancements that's going to happen over the next 6 months here. We also plan to introduce DNS egress filtering, some advanced IP address management for consumers that need a little more flexibility in how they use sparse IP address pools. Finally, we want to make sure that Antrea can play well with the legacy compute world, and make sure that things like external endpoints and such can be treated as first-class endpoints when declaring policy within Antrea. And so we plan to do that and provide other extension mechanisms as well. In terms of flow export, one of the things that we want to provide is a great capability for auditing, so that we can show exactly which connections are being made in a cluster, and track things like number of connections, the bandwidth, and look at the bandwidth in both the node bandwidth and also the service bandwidth. IPFIX is a standard format that should be compatible with a lot of consumers and operators that are going to look at this data. And we're going to provide an out-of-the-box visualization with Elastic Stack. Here's some examples of some of the screenshots that we have. Again, our first preliminary UI coming out with this features. Again, we're just beginning to scratch the surface here. And again, being able to show flows between different pods and different information about those flows. For example, in this dashboard, we have one web server pod receiving traffic from 4 different client pods. And the graph shows us how much traffic the server has been receiving from each client over time. As QoS moves out of the experimental stage and becomes a part of the product as well, and we will continue to update these metrics and provide more insight into how traffic is handled. So I want to close this and try to leave just a few minutes here for questions here at the end. We hope that you're as excited about what you've seen as we are. We want to continually evolve the networking space within Kubernetes. We have a lot of work ahead of us this year, and we really look forward to hearing from you and hopefully seeing your contributions to this rapidly moving project. We hope that we've taken steps to make it easy for you to jump in and start contributing. I think you're going to find that all of our committers, whether you're hanging out on Slack, in one of our Google groups, contributing to our GitHub issues, etc., are very responsive. And we want to make it easy for you to get involved. We've got good first issues. We've got our committers and maintainers that will come along beside you to help you, get started on an issue. So definitely check us out online on GitHub. Check out our website where we've got all of our documentation and easy to read formats. And we look forward to meeting you and helping you get plugged in to the project. So as we close today, again, we want to take just 3 minutes or so we have remaining for any questions that are out there. And again, I want to thank the CNCF, Lachlan, for hosting us today, and appreciate the time to present the exciting work that we're doing with both Project Antrea and the NVIDIA team in terms of offloading the OVS processing to hardware and accelerating CNI.
Okay, Cody, shall I run through that? We have 4 in the queue. Let's see if we can get through them in the next 3 minutes.
Sounds great.
So sounds great. I see some folks are answering them as we go as well. First one from Frederick Dang Tran. Is there a scalability issue due to the max number of virtual functions?
So I'll let Moshe take that.
Oh, basically, like I said, the maximum number of virtual functions, it depends on the next vendor. There are scalability issues, but basically the idea, as I showed you, you depend on what are the workloads. We assume not all the workloads will be required offload capabilities. So, and you can mix the pods. So some of them can still use the VTH and some of them can be the offload ones. So hopefully that answers the question.
I just want to add quickly that so with our latest device, we support hundreds of these virtual functions. So just FYI.
Excellent. We have another anonymous question. Could you please reiterate whether Antrea would provide implementation of external load balancers / ingress controllers like VMware NSX-T / Abbey Networks do? Thanks.
So our focus is currently strictly on service load balancing in terms of Kubernetes east-west traffic between pods. There are other solutions that can provide ingress-based load balancing. Some that we're closely tied with. Those were some commercial offerings that were mentioned, as well as there's some great open source offerings as well. So right now, again, our focus is just primarily east-west service load balancing.
Excellent, thank you. And that's all we have time for. I see there's one or two more questions in the queue. Please connect via what's on screen here with the project and you'll have all your questions answered. I would love to thank Antonin, Itay, Cody, and Moshe for a fantastic presentation. And this webinar recording will be posted later online today along with the slides, and we look forward to seeing you at a future CNCF webinar. Thank you and have a wonderful day.
Thank you.
Thank you.